In the last section, we talked about how to add and subtract matrices and how to multiply by a scalar. In this section, we're going to talk about how to multiply matrices by each other. So addition and subtraction of matrices was sort of easy because we just did it component-wise, but matrix multiplication is not done component-wise. So there's a special way that we define matrix multiplication, and we'll see at the end of the section when we do some applications why we might want to define it that way. So what we're going to start with is a row matrix times a column matrix. This is going to be our building block of how to multiply matrices by each other. So if I want to multiply a row matrix times a column matrix, what I do is I take the first entry of that row and I multiply it by the first entry times the column, in the column. The second entry in the row times the second entry in the column. And then the third entry in the row times the third entry in the column. And I add all of those numbers together. So I end up with 4 and 10 and 18. So 14 and 18 is 32. So the product of this row matrix times this column matrix is just the number, the single number, 32. So let's kind of write down the general steps. In general, to multiply a row matrix times a column matrix, we multiply corresponding entries and add the result. The results there. So let's go ahead and do one more example. Let's say I wanted to multiply 5, 6, 7 times 1, 3, 4, 8. If I started trying to do this, I'd multiply the 5 by the 1, the 6 by the 3, the 7 by the 4, right? But then there wouldn't be anybody to multiply by the 8. So this doesn't work. So if I think of this, this was a 1 by 3 row matrix, and this was a 4 by 1 column matrix. If these two numbers are not equal, then it's going to be impossible. So we can only multiply a row matrix by a column matrix if the number of columns in the row matrix is equal to the number of rows in the column matrix, or if those two inner numbers match each other. So then that one's not going to be possible. So let's go ahead and do one more possible example. So I'll do 5, 7, 8 times 1, oops, don't want to put it in commas, it's not usually used when we're doing matrices. Oh man, I almost put it in the wrong order. We can't do it in this order. We have to do it in the other order. So let's go get back on track here. Oh man. We want to have 5, 7. We'll just do a 2 by 2 or a 2 by 1. 1 by 2 times a 2 by 1. 11, 2. Right, so if I look at the sizes here, I have a 1 by 2 times a 2 by 1. These numbers match, so we're good. We can actually multiply these, right, because their entries match up. So I'm going to get 5 times 11 plus 7 times 2. So that gives me 55 plus 14, which is 69. So I can multiply those two together to get 69. Ooh. So let's look at an example from the book, which tells us why we multiply rows and columns of matrices the way that we do. So let's suppose a baker wants to make sugar cookies out of flour, sugar, butter, and eggs. Each batch of cookies requires 10 units of flour, 5 units of sugar, 7 units of butter, and 15 units of eggs. And then the cost per unit of each of the items is $2, $3, $7, and $4 respectively. So the first thing that I'm asked to do is to write a row matrix, which expresses how much of each ingredient is used in a batch of sugar cookies. So if I was going to write out that row matrix, we have a nice long row here, and let's list out what those ingredients are. So we have our flour, sugar, butter, and eggs, right? This isn't part of the matrix, it's just to help us make the matrix. And then in that matrix itself, we'll put the values. So each batch of cookies requires 10 units of flour, 5 units of sugar, 7 units of butter, and 15 units of eggs. Now we can go on to part B. So I want to write a column matrix. And that's going to represent the cost of each unit of ingredients. So we'll have the cost of flour, sugar, butter, and eggs. We want to keep them in the same order that we kept them in before. And then I'll list out the costs: $2, $3, $7, and $4. And now let's think about how we would calculate out the total cost for a batch. If I'm going to try to figure out how much it's going to cost to make a batch of cookies, well, I need to think about how much it costs for each ingredient. So for the flour, I know that I use 10 units of flour times $2 per unit. And then for the sugar, it's 5 units of sugar times $3 per unit. For the butter, it's $7, or 7 units and $7. And then for the eggs, I need 15 units, and then it's $4 per unit. All right, so what I would do is I would multiply all of these numbers together, and then add them all up to find my total cost. That's exactly what we do when we multiply matrices. So matrices are sort of designed, and matrix multiplication is designed to be able to take into account this sort of operation that we'd want to do. So when I multiply these, remember that we multiply the components. So I get 10 times 2 plus the next component, 5 times 3, plus the next component, 7 times 7, plus the last component, 15 times 4, I get that 144. And the reason we multiply the way that we do is so that we can kind of get this nice application. Right? Somebody had to decide that this was the way that we were going to multiply matrices. And they made that decision based on the fact that we wanted to have a nice outcome. We wanted to have a nice application of that. And this is that application that we want. So now that we've talked about multiplying a row matrix by a column matrix, we can move on to the more general setting where we're going to multiply two matrices together. So the first question we want to ask is, which matrices can we multiply? So I'm going to use a couple of variables here, but then we'll sort of see some examples of that. So I need to think about the sizes of these matrices in order to determine whether or not I can multiply them. So I don't know what A is, but let's say it's got M rows and N columns. And then we'll use different letters over here. So maybe we'll say that B has P rows and Q columns. So if I want to consider what A times B is, then I need to think about the fact that A is M by N, and B is P by Q. This multiplication is only going to work similar to the case where I'm multiplying a row and a column matrix is if these two numbers are equal. So matrix multiplication is only defined if those two inner numbers, n and p, are equal. Then I'm going to get out some matrix here, and the size of that outer matrix, right, so this n and p, we're going to hope that those are equal. If they are equal, the resulting size is going to be given by those two outer numbers. So the resulting size is the outer numbers. So the inner numbers must be equal, and then the outer numbers will tell you the resulting size or order. Okay, so first let's check that we can multiply the two matrices below, and then we'll talk about how to multiply them. So my sizes here are 2 by 2 and 2 by 2. The inner numbers here are equal, so that's good. That means I can multiply them. And then the outer numbers tell me the size of the answer. So my resulting matrix, when I multiply these, will also be a 2 by 2. Okay, so that means it has 4 different numbers here. Let's go ahead and color code them. I need to do 4 different operations to get these 4 different numbers. And what we're going to do for each of those is a row by column operation. So if I look at this first entry, it's the first row, first column. So that tells me that I should take the first row of my matrix and multiply that by the first column. So I'm actually going to just write that in there. So I need to multiply 1, 2, there shouldn't be a comma there, by 5, 7. And whatever number I get from doing that multiplication will be the entry that goes there. Let's go ahead and kind of write these all out. So the next one, I'm going to still be, this guy is still in the first row, which means I still use the first row of my matrix, but it's in the second column, so that means I use the second column of the second matrix. So that would be 1, 2 times 6, 8. Okay, down here, this is the second row, first column of the matrix answer. So what I would need to do to get that is go to my second row of the first matrix and the first column of the second matrix and multiply those together. So I do 3, 4 times 5, 7. And then finally, this last entry is the second row, second column. So in order to be able to calculate that, I use my second row, second column, and I multiply those two together. So I'm going to multiply 3, 4, which again, I shouldn't have a comma in there. Get rid of that. And I don't like honoring my commas here. 3, 4 times that 6, 8. Okay, now I actually have to do out these calculations. So remember to multiply here. I need to multiply 1, 2 times 5, 7. So this row times this column. I multiply the 1 times the 5, and I add that to the 2 times the 7. So let's go ahead and write that out. So I have 1 times 5 plus 2 times 7. I'll calculate out that number. Next, I'm going to have 1 times 6 plus 2 times 8. But that's in a completely different entry, so it doesn't get added to my first entry. Down here, I've got 3 times 5 plus 7 times 4. And over here, I'm going to have 3 times 6 plus 4 times 8. So we can actually calculate out now what all those numbers are. So I should get here, when I add those, 5 and 14 is 19. 16 and 6, 16 and 6 is 22. 15 and 28 is 3, carry the 1, 43. And then 18 and 32 is 50. So that is the product of those two matrices. It sometimes takes a while to get comfortable with this process of matrix multiplication. So I encourage you to try some of these on your own and then come back and compare what you get to what I get, and then listen through the video, the explanation if you need to kind of get the process down more. So first, I've got three matrices here, and what I want to do is I just want to go through and think about their sizes so we can determine which ones we can and we can't multiply. So A is 3 by 2, B is 2 by 2, and C is 2 by 2. So if I try to do A times B, I get a 3 by 2 times a 2 by 2. My inner numbers match, so that means I can multiply. My outer numbers will tell me the size of that matrix. So when I multiply A times B, I should get a 3 by 2 matrix. So I should be able to get something here, which will also be a 3 by 2. But if I tried to switch the order and do B times A instead, then I'd be multiplying B, which is a 2 by 2, times A, which is a 3 by 2. And here, these are not equal. So that means I can't multiply. One thing I could do, though, remember we talked about transposes. If I do B times A transpose, then B is 2 by 2. A transpose switches A's rows and columns, so that's a 2 by 3. Now these two inner numbers are equal, so I can multiply those, and the resulting matrix would be a 2 by 3. All right, so it's important to check whether or not we can actually multiply these before we actually get down to multiplying. So let's go ahead and just multiply some matrices. So I want to do A times B. So I'll write out what we're going to do. I'm going to try to color code this so we can kind of keep track. So A is 1, 2, 5, 6, 3, and running out of colors here, 1. And B is let me write out B. We'll also color code that 1, 2, 5, and 7. Okay, so now in order to multiply these, I want to do row by column. So for the first entry, I need to look at my first row of A and times that by the first column of B. So I'm just going to write out those different numbers. I'm not going to write it out as rows and columns. So we'll remember here that the answer should be a 3 by 2. So maybe we can give ourselves the different spots that we're looking for. And for this first spot, I need to do that first row of A times the first column of B. So I do 1 times 1 plus 2 times 2. Sorry, messed that up. Let me go back. I was looking at the wrong stuff here. So 1 times 1, that was good, but then I'm doing the 2 times, this 2 needs to be times by this 5, because it's the row times the column. So 2 times 5. Okay. So I'm going to now just go ahead and get rid of this here, because we're not on that row and column anymore. guess I could have left the row. And now for my next entry, I need to do row by column. So I'll do 1 times 2 plus the 2 times the 7. And then we move down to the next row and column. So I don't want to do this row and this column. We'll move down to the next ones. So we do maybe this row and this column. Okay, so let's go ahead and do that. So I get 5 times that 1 plus 6 times that 5. Now I move over to the same row, but the next column over. So same row, but let's look at this column instead. So when I do row by column there, I get 5, oops, don't want that, 5 times that 2 plus 6 times that 7. Okay, now we can move down to our last row. So we'll move down to our last row, first column. So I'm looking here at the last row, first column. I'll do that 3 times, whoops, daisy. 3 times that 1 plus 1 times that 5. Whew, so many colors. And then last entry, last row, last column. So I'm going to move over and do last row and this column. So we end up with 3 times that 2 plus 1 times that 7. Okay, so I've got down all of the calculations. Now we can actually calculate those out. So let's go ahead and do this math. So I have 1 plus 10, 11, 2 plus 14, which gives us 16. And then we have 5 plus 30, 35, 10 plus 42, 52, 3 plus 5, 8, and then 6 plus 7, which is 13. So then this will give us the product of A and B. That's that 3 by 2 matrix. All right, so let's do a couple more examples. So let's say I wanted to multiply B times C. I'm not going to go color code this one, I'll just kind of write it out. So I have 1, 2, 5, 7 times 2, 1, 3, 2. So these are both 2 by 2 matrices, so I can multiply them because those middle 2's match up. And then the answer should also be a 2 by 2. So I go row by column, so I get 1 times 2 plus 2 times 3. Row by column, 1 times 1 plus 2 times 2. Row by column, 5 times 2 plus 7 times 3. And then row by column, 5 times 1 plus 7 times 2. So I end up with 2 plus 6 is 8, 1 plus 4 is 5, 10 plus 21 is 31, and 5 and 14 is 19. I'll make that 31 slightly more readable. And that would be the product of C times B. Okay, so let's do one more. Sorry, that was B times C. Let's actually look at what C times B is. So that's going to be 2, 1, 3, 2 times 1, 2, 5, 7. So again, I have to do row by column. So I end up with 2 times 1 plus 1 times 5. row by column, 2 times 2 plus 1 times 7, row by column, 3 times 1 plus 2 times 5, and then my last row by column, 3 times 2 plus 2 times 7. So if we go ahead and multiply these all out, we get 2 plus 5, 7, 4 plus 7, 11, 3 plus 10, 13, and 6 plus 14 is 20. Okay, so one thing that we should notice here is that I did B times C and C times B, and I ended up getting different values. All right, so B times C is not equal to C times B. With numbers, you can multiply them in any order. Right, 5 times 6 is the same as 6 times 5, but that's not the same as for matrices. So matrix multiplication is not what we call commutative. So commutative just means you can change the order and you get the same thing. Sometimes C times B does equal B times C, but not always. So let's look at some more examples of when we might use systems, or when we might use matrices. And the first example we want to look at is systems of equations. So let's do out this matrix multiplication problem to kind of see how matrices can be related to systems of equations. So I have this matrix of numbers here, and I want to multiply it by this matrix of variables x and y to see what I get. So I'm going to do my typical row by column. So I've got 2, 3 times xy, so 2 times x plus 3 times y. And then I'll do my next row column. Right, there's no more columns, so I just have to go down to the next row and multiply that by this column. So I get 1 times x plus 2 times y. Right, we could have maybe checked before. This is a 2 by 2 times a 2 by 1. So these match, and I end up with a 2 by 1 matrix. So I have a matrix. It's got one entry on the top and then one entry below that. These entries kind of look like the entries that you might see in a systems of equations, right? So this entry is like the first equation here, and then this second one would be like the second, well, part of the equation. It's only going to become an equation if I set it equal to something. So maybe I can take that and now set that equal, right? I know that is going to be those two expressions, so maybe I set that equal to something like 5, 3. So let's think about what this translates into. We said if we multiply these first two, I end up with 2x plus 3y, and then x plus 2y, and that would equal that 5, 3. Now, if we go all the way back to the beginning when we were talking about matrices, we said the only way that you can have two matrices being equal to each other is if the corresponding entries were equal. So I would have to have that first entry equaled 5 and this second entry equaled 6. So this only works if 2x plus 3y equals 5 and x plus 2y equals 3. So an equation of this expression, which is called a matrix equation, that is the same as this system of equations over here. So what we're going to see is that if we change a system of equations into a matrix equation, we're going to be able to use matrix tools to help us solve that. But for right now, we just want to be able to change systems of equations into matrix equations. So how do we do that? What we need to do first is figure out what that first matrix is. So I just look at the coefficients of each of my variables. So you got to make sure the x ones are first and then the y's. And then I just list out those coefficients, 3, 2, 5, -7. And then I'll put the variables next. So I have x first and then y. So I'll put my x and then my y. And we can check that if I do that matrix multiplication out, I'm going to get that left-hand side of my expression. That first equation will be on the top, and the second one will be on the bottom. And now this just needs to be equal to whatever it was equal to over here, so that 8, 3. So I can translate a system of equations into a matrix equation this way. This starting matrix is called the coefficient matrix. And then we can use our matrix tools to help solve that system of equations. When we do this, we usually call this coefficient matrix A, this matrix of variables X, and then this solution part B. So you'll maybe see in the web assign, they'll ask you for A, X, and B. So you would just put in the coefficient matrix as your A, you put in just X and Y as your X matrix, and then you'll put in this 8 and 3 as your B matrix, or whatever numbers you're given in the problem. All right, so let's say our Toy Story characters, Woody, Buzz, and Jessie, are all at a picnic. Woody has two hamburgers and 1 serving of potato salad. Buzz has 1 hamburger and 2 servings of potato salad. And Jessie has 3 hot dogs. And we want to know how many carbs, fat, and protein each person gets. So we could go through for each person and then calculate out for each of their different types of foods how much they get of each of those. But again, this is just an example of where we could use matrices to help us. So what I want to do is I want to make 2 different matrices. My first matrix, A, is going to tell me for each person, so I'm just going to label my rows and columns. So I'm going to have Woody, Buzz, and Jessie. We just need to make sure we keep them in the same order. It's going to tell me which food they have. So if they have hamburgers, potato salad, let's do in the order that they're listed on the side there. So hamburgers, hot dogs, and potato salad. Okay, so now I'll actually fill in my matrix A. So Woody had 2 hamburgers and 1 serving of potato salad, so he had 0 hot dogs. Buzz had 1 hamburger and 2 servings of potato salad, so he didn't have any hot dogs. And then Jessie had 3 hot dogs and then nothing else. So I can get this matrix that represents sort of the different foods per person. And then I'm going to make a second matrix, B, and my second matrix is going to have the different nutrients per food. So I'm going to list the foods in the same order I listed them before. So hamburgers, hot dogs, and potato salad. And then I'll list the nutrients, fats, carbs, and protein. And then we can go ahead and fill in this matrix. So hamburgers have 10 grams of fat, 30 grams of carbs, and 13 grams of protein. Hot dogs, 23 grams of fat, 13 grams of carbs, and 9 grams of protein. And then potato salad, 20 grams of fat, 28 grams of carbs, and 6 grams of protein. So now that I have these 2, we can multiply them. And I want to really think about what's happening here. So if I think about my A and my B, I'm going to represent sort of the rows and the columns by these words. So A is sort of people by food, and B is food by, we'll say, nutrients. Maybe that's not exactly the right word. Now I have that the food parts, those match up so that I can multiply these, right? They're both foods, so that kind of makes sense. And what I'm going to get left with is my people and my nutrients. So that when I actually multiply these 2 matrices together, A times B, the resulting matrix should still have my people here. So I'll still have Woody, Buzz, and Jessie. And I'm going to have my nutrients along the top. Fat, carbs, and protein. Okay, so we actually can do out this matrix multiplication here. So I can go row by column, and I get 2 times 10 is 20, 0 times 23, and 1 times 20, so that's another 20. So I get Woody had 40 grams of fat, and that makes sense, right? He got 20 grams of fat from this 2 times this 10 grams of fat, so 2 hamburgers at 10 grams of fat each, and then 1 thing of potato salad at 20 grams of fat. So this matrix multiplication is doing exactly the calculation we need to do in order to calculate this out. So let's kind of go through here and calculate out each of these. So I moved my next row and column. So maybe we'll do this row, second column, and I get 2 times 30, so 60, plus 0 times 13, and then 1 times 28, so 60 plus 28. And then the next one, same row, last column, I'm going to get 2 times 13, 26, plus 0 times 9, and 1 times 6. Okay, and then I can go through for each of these. So now I'll go to Buzz. So I'm looking at my second row here. I need to multiply that by the first column. So I get 20 plus 40, and then second row, second column, 30 plus 28 times 2 is 56. And then second row, last column, 13 plus 12. And then we can go on to Jesse. So for Jesse, I'm looking at my last row here, and I need to multiply that by each of these different columns. So if I do last row, first column, I get 23 times 3, and 0 times the other things. Last row, second column, 3 times 13, and last row, last column, gives me that 3 times 9. So I could calculate out all of these different numbers to figure out the nutrients per person.